Now let's look inside a solution and catch a picture of what's actually going on. And again, this is extending our analysis of equilibria and free energy in acidic solutions. And we start by writing our acid reaction in the general form as HA in the aqueous phase, and we are going to react it with our good friend water, which is in the liquid phase, and that's going to set up an equilibrium that gives us the product, which is the A anion that came from the acid after the extraction of that H+, and the other product, of course, is H3O+, also in the aqueous phase. Now, we know what our equilibrium constant is. It's our Ka. That's equal to our H3O plus and our anion A minus. And that equilibrium constant then is divided through by the initial concentration of HA, the acid, as it proceeds forward to equilibrium. So the quantity that we put in for each one of those species refers to its concentration at equilibrium. All right, now we have this beautiful symmetry in the Bronsted-Lowry formation of an acid and its conjugate base. So let's just identify this in general, because we have our aqueous phase acid reacting with our water in the liquid phase, creating the equilibrium for which we have just calculated the equilibrium constant. And we have the anion resulting from the extraction of H+, that's in the aqueous phase, and our H3O+. So we start with our acid, and we pair this up with the conjugate base. So in this case, we link the HA to the A anion. So we have our acid and our conjugate base. And then in this case, water is the base, and it pairs up with the H3O+, which is the conjugate acid. Now it's interesting to look when we run over a range of equilibrium constants, that is acid ionization constants, because Ka can be very large or it can be very small. Now for a strong acid, Ka is large, and let's see what that solution looks like. It means that the reaction has gone almost to completion to the right, that is, in the formation of our H3O+ and A-, but look what a large fraction of the original reagents end up in the form of H3O+ and the anion of that acid, a huge number. In a weak acid, we have the fact that that acid equilibrium constant is very small, and in that case, we have a very limited number of cases where that reaction has gone from reactants to products. So every time we think of a weak acid, we want to look into the molecular structure of what that looks like. And for strong acids, we have virtually complete conversion of the initial acid to the H3O+. So that allows us to analyze the case for both a small acid equilibrium constant and a large one. And it's always important to keep in mind not only the Gibbs free energy surface, but also to picture in your mind what that solution actually looks like. Now we come back again to our link to thermodynamics, and this is another aspect of acid-base reactions that's always important to keep in mind. And we know for a weak acid that the acid equilibrium constant is much less than 1. Now, that means that a reasonably small fraction of the products have gone from reactants to products. But a strong acid is one in which you form virtually a complete conversion of reactants to products. So when we sketch out a general Gibbs free energy surface for an acid reaction, we start out with our initial acid that we drop into water, and then we watch what happens on a Gibbs free energy surface. So we're tracking basically this reaction of HA plus water going to the anion plus H3O plus. And the first thing we recognize is that it's a downhill run for which delta G is less than 0. And that part of the Gibbs free energy diagram, we know exactly how to calculate that because we learned how to calculate delta G under non-standard conditions. That's equal to delta G under standard conditions plus the gas constant times the temperature times the log of Q. And in this case, of course, we can write the expression for Q because it is identical in functional form to the equilibrium constant, except we remember that Q refers to the situation when we are not in equilibrium. So, but I can write the functional form of Q. It's the anion from the acid times H3O plus divided through by the initial acid concentration. So this downhill spontaneous movement from reactants toward the product case ends up at the point where we've reached the equilibrium position in this reaction. And at that point, delta G is equal to 0, and the reaction ceases to shift in its concentration. Now we have to remember that the equilibrium point is the point where the relative concentrations of reactants and products has stabilized. That is, it does not change with time. But that doesn't mean the reaction isn't going on. In fact, there's this furious conversion of the acid plus water to H3O plus, and the back conversion of H3O plus back to the acid. It's a very, very dynamic equilibrium. But we also remember something very important, that if we were to start with the anion of that acid and H3O plus, we have delta G under non-standard conditions is less than 0, and that means the reaction will move from right to left, that is converting products into reactants until it finds the magic point, the equilibrium position in the reaction. So we always keep in mind then that the relative concentrations of the products and the reactants are driven by this Gibbs free energy surface. And we know that at equilibrium, delta G is equal to 0, but we also know that Q is equal to K equilibrium at that case. But under the conditions of an acid reaction, that Q goes to the equilibrium point, but the equilibrium point is set by the K sub A, the acid equilibrium constant. So when delta G is equal to 0, we can plug in the value for Q into our general expression for delta G under non-standard conditions and immediately deduce the fact that delta G under standard conditions is equal to minus RT log K acid. And that is the conversion of the general form of Gibbs free energy to the specific form for an acid reaction. So let's take a peek again at this acetic acid reaction. We know that the carboxylic group, which is characterized by this double bonded oxygen into the carbon, bonded into the OH at the end, and the electronegativity of the oxygen has delocalized electron density away from the hydrogen, exposing it to attack by the negative end of water, which succeeds in stealing that H plus from the acid structure, producing the acetate anion and our product H3O plus in the aqueous phase. So we started with a weak acid, and that produced a strong base because our conjugate base is the acetate anion. And so a weak acid results in a strong base, just as a strong base results in a weak acid. So this symmetry that's intrinsic to this formulation of acid reactions is extremely valuable because it allows us to look at the relationship between the strength of an acid and its conjugate base and vice versa, a base and its conjugate acid.